Hi guys, this is Vineet, and in today's video we will discuss about the execution plan generation process and query optimizer in SQL Server. This is part 2 of this video. If you have not watched the part 1, please watch the part 1 before watching this video. So in this video we will particularly cover the query optimizer, the optimization process in general. Uh, Before proceeding ahead, I would request you guys to please go ahead and immediately subscribe to my channel. There is a subscribe button below this video. Click on that subscribe button. It will give you a bell icon. Click on that bell icon. Select all notifications to get notifications regarding all my future videos. Let's move ahead. There are some points to remember while watching this video. Please watch this video till the end to gain better clarity of the concept, and if it's possible for you, please watch the video twice or as many as times as you want until the concept gets cleared. Perform any exercises mentioned in the video in your test and lab environments only. Do not touch any production environment or production databases. And we would like to know your thoughts regarding our videos. So guys, please do share comments with us. Any suggestions, any requirements, any your day-to-day experiences with SQL Server, any situations where my videos have given any help to you. And also anything related to SQL Server that you would like to share in general. Do post us your comment. We eagerly wait for them. And we love to read them. Alright, let's move ahead, and I have created some playlists for you to watch. Some of the playlists are database design playlist, table playlist, business continuity playlist, indexing, performance tuning, and integration services playlist. These playlists have vast variety of videos, so I would recommend going through all these playlists. If you want to learn gain the knowledge inside a particular domain, for example, if you want to learn about integration services, I would recommend going to the integration services playlist and watch out all the videos. So it's better than watching videos randomly that get posted on my channel on a day-to-day basis. So I post videos on wide variety of topics. So it will not be useful if you watch videos in a random manner. It's better if you want to gain knowledge in a better way. The recommendation is to go through a playlist completely before moving on to another playlist. I posted around 170 videos on my channel, so my channel has lots of videos. So channel link page is given below, and the link is also available in the video description. Although also the links for all the playlists are available in the video description area, so please check them out. Now let's come back to today's topic, where we will cover the optimization process today. Earlier we have covered various other concepts as well, so let's quickly go to notes. So earlier we talked about the process in general. So the first step is that query is fed to the parser, which generates the parse tree, and then the object binding process is done. And after object binding process, query processor tree is generated, and which is fed to the optimizer. So this is the point where the optimization process starts. So let's talk about optimization process today. So let's discuss it. So starting with the optimization process in general. So what I would say, its optimization process is an amazing piece of software. So this is the first point. It's an amazing piece of software. And if we don't use any debugger, we won't see it in action whether any optimization is being performed. So without a debugger, we cannot see the optimization process happening, right? So this is another point. Now the third point is, so if we want to see the optimization process, we need to use the debugger software. Until we use the debugger, we cannot see any optimization happening in front of our eyes. However, we can see the result of the optimization process. we can say, however, we can see the result of the optimization process in the form of or in the execution plans. We can see the result of the optimization that it creates. So optimization process basically creates the execution plans, right? And then that execution plan is then fed to the storage engine. All right, guys. And so execution plans get generated by the optimization process, which is basically a result of the optimization process. All right, and let's move ahead. There is also concept of there are other things which can be used to observe the aspects of the optimization process. Those are dynamic management views. We will talk about them later. So dynamic management views and extended events, which is another topic, can be used to observe the aspects of the optimization process as well. All right. So in this video, though we will not be examining any code with the debugger, let's start talking about the optimization process now. So basically the role of optimizer is to provide a, I would say, good enough execution plan to us as quickly as possible. So this is the role of the optimizer, and there are some steps happens during the optimization process. So first simplification happens. After simplification, trivial match planning happens. So first step is the simplification, second plan is the trivial match plan, and third is the optimization process so we will go through them one by one. So the first thing is simplification happens, then a trivial match planning is done, then the optimization phases are performed. So let's talk about that. So optimization phases, if we talk about there are multiple optimization phases, and there can be generation of one execution plan, or even more than one execution plans can be generated. All right. For any parallel optimization, multiple plans can be generated, and these plans are saved to the procedure cache. Let's discuss about them in detail. Discuss about each step in order to understand how the optimizer arrives at an execution plan. So we will start with the simplification process. So let's copy this out. Sorry guys, let's copy it and paste it, make it a heading. All right, so we are talking about simplification process now. So if we talk about simplification, the first step in optimization process is called simplification. So it is the first step in the optimization process. All right. And in this process, basically, the optimizer ensures that all the objects that you reference in a query in your query maybe are actually in use. So during the simplification phase, the optimizer ensures that all the objects that are referenced by the query are actually in use. All right. And after that, what happens? Statistics and row counts begin to be gathered and used. And basically the step simplification step, this step also looks at constraints, any constraints such as foreign keys as well, right? And all of this is taken together and we can see the optimizer actually change what is being processed. So all of the above items are taken together. We can see that optimizer actually change what is being processed. I will give you an example for this. So let's take an example, right? So you may write a query with a four table join. So for example, if we or maybe you may write a query with a four table join. Let's take four table join. All right. So guys, there can be an example where we have used four query joins in a SQL query. So we may write a query with a four table join. All right. However, only, we can only select, however, we can say only two tables are referenced in the select list. So give more attention to this, guys. So we may write a query where we have joined four tables, but we are not using all of those four tables in the select list. Instead, what we are doing is we are just using two tables in the select list in this example, right? And in the select list and the where clause as well, we are using only two tables. We are referencing only two tables, right? Where clause, I would say, not list. All right. So using the constraints, the optimizer can tell that it does not need the other two tables, right? So optimizer will determine at that time that the other two tables are not required, which are not referenced in either in the select list or in the where clause. Those tables are not required. Other two tables to satisfy the query, right? And ultimately it will therefore eliminate those tables, eliminate those or them from further processing. So this is what optimizer does. So if we have written any queries with joins made on four tables, but we are not using that four table to get the data, all of the four tables to fetch the data, then yeah, query optimizer may remove the redundant tables which are not being used from the query, actual query text. So this process is known as simplification basically. So after eliminating, it is what it is doing is it is simplifying what is being simplifying what is being queried. All right. Uh, and therefore, this is the name of the step, simplification. So, guys, I hope you get the idea of the simplification process. I've given you an example what happens during a simplification process. All right. So, let's move ahead. Now, let's discuss about the other step, which is trivial match plan match. This step happens after the simplification process. So let me make it a heading quickly. Let me see which. Let's use this color. So let's talk about the trivial plan match. What is a trivial plan match? Now, when your query is extremely simplistic, all right. So if your query is so simple, it can match a pattern for which there are no options, but only one possible. So sometimes we write a query which is so simplistic and it can match a pattern for which there are no options, but this query can have only one possible execution plan. So that situation, this situation is referred to as a trivial plan. So we can say that this particular query has only one possible plan or one trivial plan. So this is what the trivial plan is. Now let's take an example of this. Let's take a table with the no clustered index. All right, which is also referred to as heap. So a table which does not have a cluster index is known as heap. And if it has no other indexes, all right. If we have this situation, we have a table with no cluster index and it is known as heap and there are no other non-clustered indexes defined on it. The only way this table can be accessed through a table scan. So when we select data from this table, so we can say the only way to access data from this table is to do a table scan because no indexes are defined on this table, right? So a table scan is required to fetch the data. Now in this situation, let's talk about this situation. Let's consider this example. So rather than even attempting to build an execution plan. So we are talking about the query optimizer here. So in these type of situation where no index is defined on the table, so query optimizer will not waste any time in building an execution plan. So rather than even attempting to build an execution plan, the query optimizer, what does it do? The query optimizer look for the query pattern. So it will check the query pattern at this point with any existing trivial plans that matches any existing trivial plans. All right. And when a match pattern is found, optimization, which is an expensive operation. Optimization, an expensive operation, is skipped entirely. So, if taking this example in view, where we have a table where no cluster indexes are defined, and it is a heap and no other indexes are defined on the table, and the only way to access data from the table is to do a table scan. So in this situation, what a query optimizer does is it looks for the query pattern. It looks for the query pattern if it is fetching a data from a particular table with no indexes. It tries to match the query pattern with the existing trivial plans, and if a match pattern is found, then the optimization operation is skipped entirely. And instead, what happens is, instead, let me give a space quickly. So at this point, instead, the trivial plan is used to satisfy the query. So no optimization process occurs here, but the trivial plan is being used to satisfy the query at this point. All right. So we see only the trivial plans being used only in the cases where we have extremely simple queries. All right. So only if we have extremely simple queries, in those situations only the trivial plans are being used. And we can see the plan if it is marked as trivial in the properties of an execution plan. So we will show it to you shortly to see if it's a trivial execution plan. Now the next step after the trivial match plan is the optimization phases that occurs. So first one is the simplification, which basically simplifies the query. Trivial match plan is where the query text is matched against any of the trivial plans. But that happens only for the extremely simplistic queries. We have shared an example as well. Now let's talk about the optimization phases, guys. So let me write that. Optimization phases. Okay, let's discuss the optimization phases. So once it is clear that the trivial plan won't be found, so if a trivial plan is found, it is being used to satisfy the query. In case the trivial plan is not found, won't be found. So this can happen in the situation where we have a complex query where our query is not simple. So in those cases, trivial plan won't be found usually. So if the trivial plan is not found, the query optimizer will have to go through multiple optimization phases, right? To attempt to arrive at a good enough execution plan. All right. So the process gets breakdown into multiple steps. Each one is attempting to do as little work as possible. So this process, so we are talking about the multiple phases here. So this process, so it breaks down, breaks this process down into multiple steps. So now the process gets break down into multiple steps, and each step performs where each step performs its work, some little work each step will perform, and these steps are called uh, so what are these phases? So let me type so the first one is the search zero or transaction. So first step is the search zero or transaction. All right, let me make this a heading. This is extremely bad, guys. Let's take it like this. Okay. So the first step is search zero or transaction. So the first phase is either we can call it search zero or transaction. So it is called transaction basically since the type of queries that can be satisfied here are generally simple. So after the trivial plan matching process happens and no trivial plan is found, Query Optimizer takes that query text through various phases or various searches we can say, or various steps we can say. So first step, it takes the query text through the search zero or transaction phase, right? And this phase is called transaction, and it basically matches any of the query types which are generally simple. And it is called transaction since the type of query that can be satisfied here are generally simple. So for example, any of the queries like online transaction processing, or we can say OLTP style queries with very few joins and no trans transformations needed can be satisfied in this search on this or in this step, right? So this is the first phase the query goes through. Let's talk about some of the other phases. So first the query text went through the goes through the search zero transaction phase. All right. The second phase is search one phase, or we can say a quick plan phase. All right. So in this phase, more complex operations occur, such as reordering of joins. Uh, that happens during this phase. and other transformations happens as well in this phase to arrive at a good enough plan. So any reordering of joins and other transformations happen during this phase to arrive at a good enough plan. Now the third phase is search to or full optimization phase. So if we talk about this phase, so when your queries are complex, so we can say when queries are complex, they end up going through all the all three optimization. So any queries that does not get satisfied by the previous two steps get goes through the third step as well. So if your queries are quite complex, they end up going through all the three optimization steps to arrive at a full optimization. All right. So these are multiple phases in the optimization process, apart from trivial plan match and the simplification process. So the query goes to search 0, which is a transaction phase, search 1, which is where the quick plan is made, or search 2, where the full optimization is done to create a plan. Now, if we talk about the optimizer, uh, the optimizer can shorten these searches as well, heading straight to the quick plan phase or the second phase, or directly skipping to the full optimization or the third plan, search 2, skipping transaction. So it's up to optimizer to shorten these searches and head straight to either a quick plan or a full optimization plan, skipping the transaction or quick plan phase, skipping transaction depending upon the query. So it depends upon the query whether the optimizer will skip any of the searches here. It may not take the query through all the three plans. It may directly go to full optimization plan, or it may directly go to a quick plan and not performing the search at the transaction level or search 0. It's totally up to the optimizer. All right. So it can skip the transaction plan, which basically depends upon the query, its complexity, I would say. And the supporting objects, which are basically the indexes and the constraints. Depending upon these objects, the query optimizer decides whether to take the query text through all the three steps, or it may also skip some steps as well, directly go to the third step instead. All right. And these phases can decide on how to perform a join operation or access data through scans or seeks. So the role of these phases, so basically these phases we can say can decide on how to perform the join operation or access the data through scans, or seeks. So it is decided that these three steps, how the joining will be performed and how we will access the data through scan, to a table scan or an index seek maybe. All right. Now, the principal driver for most of the decisions within the optimizer are row counts. So row counts can be one of the one of the principal drivers for most of the decisions. So how many rows do we have in a table, and whether we are and if we are using that table in a particular query. If a table has generally less number of rows, table scan gets performed. But yeah, if it has a large number of rows and if an index is built on the table, yeah, the query optimizer will prefer that index can be used instead of directly doing a table scan. For shorter tables, table scans are preferable. So row count can be one of the principal drivers behind for most of the decisions. All right. So how many rows we have in a table can be one of the major drivers. And from where do we get the row counts? So basically row counts generally come from the statistics of the column. So we get row counts from the statistics of the column in the filtering criteria, such as on, having, and where predicates. So row counts basically generally come from the statistics we calculate on columns, etc. We will talk about statistics in some other videos. But yeah, row counts generally come from the statistics of the column used in the filtering criteria, such as having, where, on. All right. Now, with the statistics in hand, the optimizer begins to make choices and calculations based on how much estimated CPU, memory, and IO are necessary to satisfy the query. So, with all the statistics in hand, right? The statistics like how many indexes we have on the table, how many rows are there in the table, whatever all statistics provide information to the query optimizer. With statistics in hand, the optimization, or we can say the optimizer begins to make choices at this point, and it will also perform the calculations based on how much CPU, memory, and IO is required, or IO are necessary to satisfy the query. All right. So it tries to determine how much the optimizer tries to determine how much CPU, memory, and IO operations are required to satisfy the query. And based upon these statistics, it makes the choices regarding the plans that will be generated, that will be chosen. All right. And these estimates of CPU, memory plus IO are added up to a cost for the execution of the query. So all these estimates adds to the cost for the execution of the query. And the cost is not a measure based on your system, rather it's an arbitrary calculation made by the optimizer and is purely a mathematical construct. All right. So these calculation does not depend upon your system, but these are based on the mathematical constructs, and these are basically totally arbitrary calculations. And the optimizer will make the calculations on the number of iteration it needs to run through, attempting different plans with different strategies. So what optimizer will do at this point? The optimizer will make a calculation on the number of iterations it needs to run through by attempting different plans with different strategies. So optimizer will try to determine how many iterations it has to perform it if it uses the different kind of plans. And different kind of strategies, how many iterations are required. And at the same time, it also calculates, right? Calculates what is likely to be a least cost plan. So while going through this iterations, it tries to determine what is the least cost plan. And when optimizer finds the plan that meets all the calculated requirements, right? Requirements, it will stop any further optimization, right? It will stop the optimization process even if a better plan could be found. So once the optimizer finds a plan that meets all the calculated requirements, it stops the optimization process. There could be a possibility that a better plan is available at that point. But yeah, whenever optimizer finds the plan which satisfy all the calculated requirement, it stops the optimization process there. This is also known as we could say early termination of optimization, as the optimization process has terminated earlier. There could be a good plans which can be found if the optimizer has performed further optimization. But yeah, when the optimizer finds the plan that beats all the calculated requirements, it stops the optimization process. And you will also see that the termination of optimization, when the optimization, when the optimizer has gone through all the calculated number of iterations. At this point, it will end optimization through what is referred to as a timeout. So there is also a timeout associated with the optimizer. So after a certain number of iteration, the optimizer will stop doing the optimization. All right. Now, if a query reaches your search to step, which is the last step in the or the full optimization step, if query reaches this point, so if a query reaches search to step, which is also known as the full optimization step, it may also be evaluated for conversion from a serial plan to a parallel plan. So if a particular query text reaches the third stage, which is the full optimization stage. At this point, it is also evaluated uh, for conversion from a serial execution plan to a parallel execution plan. So this query may be evaluated for that. And it is possible to see a lot of work the optimizer is doing through the use of execution plans. Now, we will run a query to show you that. So, what we are talking about is it is possible to see a lot of work that the query optimizer, or we can say just the optimizer, is doing through the use of the execution plan. So let me show you how to check that optimizer work. We will generate an execution plan. So for that we need to write up a query. So let's launch SQL Server. Waiting for it to launch. Thereafter we will write a query. We will join various tables. Let's see what all tables have to be joined. So SQL Server is open in the background. Let's connect to the default instance of SQL Server. Let's use the AdventureWorks 2022 database. Trigger a new query. Okay, guys, let's write a slightly complex query. So you may type the code, SQL code along with me. So we are doing a select from join of certain tables. So first table will be sales dot sales order header. So we are taking the name as SOH. We are joining this with table sales dot sales order detail, and we are taking it as SOD. We are again joining it with production dot product, and we are taking it as P for product. Let's join it with production dot product model. Let's join it with product model. So we are taking it as PM. So we need to join on certain columns. So first join will be made on SOH dot sales order ID. We are joining on the sales order ID. We are joining SOH with SOT. So SOH dot sales order ID is equal to SOD dot sales order ID. And next table we are joining on, there's a product table. So we are joining on the product ID column. So here SOD dot product ID will be equal to P dot product ID. Next table we are joining on product model ID. So P dot product model ID equal to PM dot product model ID. So far we have joined 4 tables, right? Let's join some more. So let's join it with the production dot product subcategory table is there. Product subcategory. Let me see if it's there. Subcategory. Take it as product subcategory, and we are joining it on P dot product subcategory ID. Let's join on that PS dot product subcategory ID. All right, and again join it with, let's join it with production dot product category table. We are taking it as PC, joining it on production subcategory, product category ID. We are joining it with production category dot product category ID. So we are done with joins. Here we are joining approximately 6 tables. So this is quite a complex query. In where condition, we are specifying the sales order header, customer ID. So we are taking any of the products bought by customer 29658 will be the ID of that customer. Now let's define the select clause where we will select only certain columns from the table. So first we will be selecting SOH dot sales order number. Second column we are selecting is SOD, which is sales order detail dot order quantity. Let's take order quantity. Then we will take sales order detail dot line total. Then we are taking sales order detail dot unit price, and then we are taking sales order detail dot unit price discount. All right. Let's take some more column from other table. Let's take some column from products table. So product name we are taking, and we are taking name as the product name. So column will be marked as product name. And let's take product number. So we have a product number as well. So we are taking it as is. And let's select some subcategory columns. So PS dot subcategory name, as we can mark it as product subcategory name, maybe category name. All right. Let's take one more column. So that is from the PC product category table. Let's take a name, and we are taking as product category name. All right, so yeah, this will be the last column. So we are selecting certain columns upon joining around 6 tables and filtering it with customer ID of 29658. All right, so this is the query we have written. You may also write the same query at your end. All right, let's move ahead. Now, let's try to generate a query execution plan for this query. Maybe let's generate an actual execution plan. So in order to generate the actual execution plan, let's turn on this include actual execution plan button and just execute the query. So in the messages section and the execution plan section, we see an execution plan is generated for this query. If we can expand on this, so this is the execution plan that is generated, right? So this is quite a complex plan. If you see, many operations are being done in this plan. So let's see. Now we have captured the execution plan for this query. We can see some of the behavior of the optimizer here in the execution plan. All right, so we will show you how optimizer is behaving via this execution plan. And this plan is little hard to read within this context, but we don't want you to understand it all at this point. So we got a plan. Please don't try to read that plan as of now. All right, it's way too small to read. Instead of reading the plan now, we are going to focus on just one spot in this plan, the operator on the far left side of the plan. In this case, it's a select query. So this is the operator with an exclamation mark, you see. Let's focus our attention here on this operator, right? The properties of this operator are all of the information about the execution plan itself. So if we take a look at the properties of this select operator, this will provide the information about the execution plan itself. And this also includes information about the optimization process as well. So let's see some of the properties under the miscellaneous section. So if you right click on it and click on properties, it will show the properties on the right hand side. Otherwise, if you just point, it shows the properties, but it will vanish if you move the mouse pointer. So instead, right click on that operator and select properties, so that properties window can be opened on the right hand side. So in the properties window, let's focus on the, let me expand on this. Let's focus on the miscellaneous section. So this is the first section, miscellaneous. So it is giving out various information like cache plan size, cardinality estimation, model version, compile CPU, etc., etc., compile memory, compile time. Now, some of the information immediately on display includes the following. So let's take a look at compile CPU. It basically indicates the amount of CPU time taken, which is 46. The amount of CPU time taken to compile this plan. So it took like 46 milliseconds to create this plan. Then it shows us the estimated number of rows per execution, which is this column. So what is the estimated number of rows per execution? It is set to 7.78. So per execution, it has processed 7.78 rows. So estimated number of rows per execution, it is basically the row count that the optimizer arrived at for this query. All right, so this is basically referring to the row count that optimizer arrived at for this query. Number of rows per execution. This is completed by the query optimizer. Now there is also an estimated subtree cost, which is 0.083. So this refers to the combined estimates on CPU, IO, and memory. So this is the sum total of CPU, IO, and memory arrived through the optimization process. So it is giving some subtree cost as well. Now that's just a sample of the amount of information gathered here for how the optimizer works to arrive at an execution plan. So optimizer checks all this information to arrive at an execution plan. So it check all of these cost, number of execution, rows per execution, estimated number of rows per execution, compile memory time, compile CPU time, total compile time. It takes all these factor into consideration while preparing the execution plan. Now we can also look to this data to see things like the optimization level. So if you scroll below, you see the optimization level over here. So here we see the full optimization is achieved, which is referring to this third pass, search to or full optimization. So in our case, as the query was complex, so the optimization has reached this particular phase, search to or full optimization, which is indicated by the query optimization this setting, optimization level. It is currently set to 4. It basically indicates to us that the query text has reached the third phase of the optimization level, which is search to or full optimization. All right, let's move ahead. So far we have checked the optimization level and the reason for early termination. Do you see a reason for early termination over here? So this is the column which is indicating the reason for early termination of statement. So the reason given is that it has found a good enough plan. So that's why the optimizer terminated early. All right. So optimizer terminated early because it has found a good enough query plan. So it gives the reason out here in this column. The top and bottom. Let's talk about top and bottom properties. I think we are good here. So we have checked the optimization level, and we have talked about reason for early termination of statement optimization. So reason for early termination of statement optimization, why the optimization process stopped early. The reason being is it has found good enough plan. Now one point is worth noting here is that when we see the property optimization level, so we are talking about this property now, and a value of full here. So we see a value full here, right? It doesn't necessarily mean that this plan went through search to. So earlier I was talking that if it is showing full over here, it indicates that the query text has reached the third phase, search to or full optimization. Well, that is not the case. So if that's not the case, then what's the case? So basically, if we see a value full over here, doesn't necessarily means that the plan went through search to. It only means that it's not a trivial plan. So full indicates here that it's not a trivial plan. All right. That's it. It indicates just that it's not a trivial plan, which is, I think, the full indicates that it's not a trivial plan. All right. So we talked about trivial plan earlier. So in this case, trivial plan was not found. So that's why it's showing us full over there. It is not indicating that the query text has reached the search to phase. All right. So it only means that it's not a trivial plan. Now, another way to observe some of the work by the optimizer is to use the dynamic management view. So far, we have shown you the properties regarding some of the work done by the optimizer. We have shown you some columns, CPU compile time information, etc., and the optimization level, and we have talked about reason for early termination of statement optimization source. These are some of the fields indicating work done by the optimizer. Now let's close that. And apart from that, there are other ways to check the work of optimizer by using the dynamic management view. Uh, there's one of the dynamic management view. Let me point that out. So let me type one of the ways to observe some of the work uh, done by the optimizer is to use the dynamic management view, or we can say DMVs, are most common term for that. So that dynamic management view is just dot DM execute query optimizer info. All right, so that dynamic management view can be used. So this dynamic view is named appropriately. Execute query optimizer info. So this DMV basically shows aggregated data about the optimization process. Let's discuss an example of how to use this DMV listed here. This DMV. Let me mark this with some color. Good color. Let's talk about this DMV, and let's ignore the spellings. So DMV is sys.dm exact query optimizer info. Let me show you an example. So let's write another query in the query window. Let's do a new query. So let's select items from the this particular dynamic management view. So it's DM exact query optimizer info. This is the dynamic management view, and we can take it as maybe let's take it as decoy to mark it in an abbreviated form. So decoy dot, let's say, takes counter column and maybe another columns. We can check. There are three columns. So occurrence and the last column is decoy dot value. These three are the only columns available in this dynamic management view. Now let's execute this statement. So it gives us some information out here, right? Which is a partial set of result from the query. It is visible in the this output. Now you can see the system I've run this on has done very few complex optimizations. So these are talking about the numbers. So number of optimizations done by this system is 714, and this dynamic management view contains the history information about all the things happened, like how many optimizations had made in this system. So if we take a look, yeah, we have done in fact quite a large number of optimization, which is 714, right? So we can tell that because there have been no search to operations. So we see that the number of search to operations are indicated over here. So search to is indicating 0. So that basically indicates that we have done very less full optimization. So search to was similar to the thing I was talking before. So this is search to indicated by this particular column, this one. So there were no search to. So query any of the queries executed in this environments in the past haven't went up to this stage, search to or full optimization. Yeah, the queries went through such for one phase, or the quick plan is the number of queries went through that is around 403 queries went through that, and through search 0, 95 queries have went through search 0. All right. So 95 times this operation has occurred, and it has a value of 1. All right, let's not read through this. So we can tell from this that there were no such two operations, as it is 0. Now you can see the other operations that have been done and the estimated time needed to accomplish them. So if we see around 403 search operations were done, and the time taken to complete those 403 searches were 0.003. I don't know whether that's millisecond or second. That should be milliseconds. All right. And let's move ahead. This information is only of limited use, but it is good to know where to go and get that information. So this is please remember this dynamic management view to get these informations. So, so it is good to know where to go to get this information in the event that you need to understand some of the processes that the optimizer is going through and the load it is placing on your system. All right. You could also run this code before and after the query in order to see the types of optimizations that occurred on the query. So if you execute any other complex queries in the system, you can check out these stats to see if the counters have increased or not. All right. However, you need to do this on an isolated system. So, but yeah, these tests or these counters should be checked on an isolated system, not the system available to public. If you want to investigate a particular query and what changes it is making to these counters, make sure you are checking that on the isolated system, because if a system is available to public, then many queries will be executing against the system, and it will be difficult for you to track what a particular query is adding, how much data is particular query is adding to this counter. So it would be difficult to track. So perform these checks or use this dynamic management view on a system which is isolated if you are trying to test certain queries and how that query is increasing the counters. And if you want to check the stats after running a particular query, make sure you are doing that on an isolated system. Now let's talk about the generation of let's go to next topic, guys. So next topic is the generation of or generating the parallel execution plans. All right. So let's cover this topic, and all right. So basically parallel execution plans are created when the plans become complex enough. So we can say when the plans become complex enough, they may be benefit, or they may get benefit from parallel execution. All right. So what is parallel execution? Parallel execution is when more than one CPU is available to SQL Server. So parallel execution can only be done if more than one CPU have written CPI, so it's CPU. If more than one CPU is available to SQL Server, parallel execution can be performed, right? So more than one is put to work on a single query. So if we have multiple CPUs available to SQL Server, we can put all of those CPUs in executing a particular query if that query is quite complex. So we can take advantage of parallel execution. All right. And if we talk about parallel execution, it's an expensive operation. So let me write that. So parallel execution is an expensive operation. Do keep in mind. All right. So it's an expensive operation so far. That is what we have discussed. And if you want certain query to get benefit from the parallel execution, we can let that query go through it. So that is also the fact. Some queries can be executed in a parallel fashion as well, but they actually run slower because of the process. So keep that fact in mind. Some queries can be executed in parallel fashion, but they actually run slower because of the parallel execution process. Now, when the optimizer is deciding on whether or not a complex query will go parallel, it takes a number of factors into consideration. So, how do query optimizer decide whether to take a particular complex query through parallel execution? So, when the optimizer is deciding on whether or not a particular complex or a complex query, whether or not a complex query goes through parallel execution, it keeps in mind the following factors. And what are these factors? Let me mention them. So, optimizer look into various factors. Let me name them one by one. So, whether a query will go parallel will depend upon CPUs available to the SQL Server. That is one of the factor. If more than one CPU are there on the machine, how many CPUs are available to the SQL Server? What is the SQL Server edition? So, not all the edition of SQL Server support the parallel execution. How much is the available memory to the SQL Server? And what will be the cost threshold for parallelism? All right. Another factor it consider is query being executed. What is the query? What is the query text that is being executed? That is also one of the factors. Number of rows to be processed is one of the another factor. If the number of rows are less, there is no point in doing some parallel execution. And we will also the optimizer will also take a look at active concurrent connections to the server. So it also takes that into consideration. Another thing it takes into consideration is max degree of parallelism. So this is a setting inside SQL Server. We'll talk about that shortly. So these are some of the factors optimizer take into consideration before it consider taking a complex query through the parallel execution. Now, the three most important of these factors are the actual number of. So let me tell you which factors are important. So this one is important. So CPUs available to SQL Server is of first importance in deciding whether a particular query will go parallel. Then the second factor which is important is the max degree of parallelism. This factor is very important. Third factor which is important is cost threshold for parallelism. This one. So this factor is also very important in deciding whether a particular complex query will go through the parallel execution. Now, if there is only a single CPU or a single virtual CPU on a NUMA node available to SQL Server, then you won't see any query go parallel. So obviously, if it's a single CPU system or a single virtual CPU system on a NUMA node available to SQL Server, then we don't see any queries go through parallel execution. We can also restrict the parallelism and the number of CPU used by it through the max degree of parallelism setting. So this is the setting I was talking about. It can be controlled. So this is a setting in SQL Server. So this setting is used to restrict the parallelism and the number of CPUs that will be used for the parallel processing. Setting to a value of 1, if we set this value to 1, value of this setting to 1, what happens? If we set that value to 1 for this setting, it will eliminate all the parallel execution. So if this setting is set to 1, it will eliminate all the parallel execution. But this is not recommended. So setting this setting to 1 is not recommended. And to control the max degree of parallelism, we may have to use the server setting. All right. So what is that server setting? Let me show you that. So let's go inside SQL Server. Let's execute a new query maybe. So we need to use the master database to check this. So let's move on to master. We can execute the stored procedure sp configure, right? To see the configuration settings of the server, various configuration settings of the server. So by default, this is an advanced setting. So this setting will not show up over here. So the setting name is max degree of parallelism. So it is showing up over here. So without even, I think the advanced settings are turned on. So that's why we are able to see this option. Otherwise, show advanced option setting should be set to 1 or turned on. So this is the setting we are referring to. So right now minimum it is set to 0 and maximum it is set to 32767. The configured value is 8 and the run value is 8. So the maximum number of CPUs I have on my machine is around 8. Let me show you that. So that's why this setting is configured to 8 CPU. So you see we have 8 logical processors over here under the logical processor section. So I think that's why the system has configured this setting to 8. So it can use any of the complex queries. An optimizer can decide for any complex query. The maximum degree of parallelism supported is 8 CPUs can work on a particular query. So that is the max setting defined for this query optimization. Now, when you change the setting, we can change these settings as well, right? We can change it through sp configure option. So let me change it to 6. Let me show you how you can change this setting to 6 instead of 8. So in order to do that, you execute the same stored procedure and give the setting name. So max degree of parallelism. All right, and let's set it to value 6. So that will mean that only and after that you need to type the reconfigure keyword to reconfigure it. Let's execute it. So it's executed. Now let me check what all options are there. So let's do sp configure and check what all settings are configured. So let's check on max degree of parallelism, starting with them. So max degree of parallelism, it is now set to 6 if you check it over here. So runtime value is 6 and configured value is also 6. So runtime value is set to 6 because we have ran the reconfigure command. So it is using the 6 value currently for any of the query processing work. All right, so this is how you change these server level settings. Especially we talked about the max degree of parallelism. And whenever you reconfigure these settings, this will take effect immediately. And determining the Let's change it back to 8 first because we have 8 CPUs, so we would like to utilize all of them. All right, so this is done, and let's check it once again. So it is set back to 8 now, and the settings almost take effect immediately if you use the reconfigure option. And determining the precise setting for this value is frequently of a great debate. And your systems and your workload should drive these decisions, not some arbitrary calculations based on the number of processors on your system. So how much this value is set to, it depends upon the workload that is present on your system, and not surely number of CPUs that are available on the system, and you want to utilize all the CPUs. And because of this, we don't want to make any precise determination here, other than to emphasize again that parallel execution of some queries is very desirable. So you want to leave the possibility on your systems, meaning don't set the max degree of parallelism to 1. Don't set it to 1, that's for sure. Now, we can also control the degree of parallelism on a query by query basis. So this setting can also be set on a query by query basis through query hints. So query hints can be used to set this particular setting max degree of parallelism at the query base query level, you can say. So the use of query hints should be very carefully regulated on the system. So we will emphasize on this point. So we will talk about query hints later, but yeah, the use of query hints should be minimal and should be regulated on the systems. Now let me give you an example where you can use where you can control the max degree of parallelism using the query hint. So let me show you how to do that. So for example, if you want a particular query to use only setting of max degree of parallelism of 2. So how you can do that? Let me rub off this system. So let's run a select query against an, I don't know if we have an example table. Let's see if we have any example table in other DBs. Table. Don't have any table here. Let's have sample. Let's say let's take a student table from here. Let's write a new query. So for example, let me show you what is there in the student table. So there are 3 rows, although this doesn't need any query optimization because the number of rows are very limited. But as an example, let me show you how you can use a query hint while fetching data from certain table. So let's select star from student, right? I'm specifying a where clause, maybe where I can say student ID equal to 3. All right. So in the end, you specify the query hints. So for example, if you want to use the max degree of parallelism of 2 for this query, then you can use the option keyword, and the setting is max top, which refers to the max degree of parallelism, and you can specify the setting. Here we want to use the 2 CPUs to uh, as max degree of parallelism for this query. So we can specify that option like this. All right, and we can execute the query in the same manner. All right. So this is how you use the query hint. So this last row is a query hint, giving hint to the query to use the max degree of parallelism of 2. All right. And if you want to more directly control which plans go parallel, the best way is controlling the process by changing the cost threshold for parallelism. So there's another setting, right? So let me show you that setting. Let's close this out. So let me do an undo so that it can give me the previous code. So this is the code. So far we have seen the max degree of parallelism, and in case if you want more direct control over which plans will go parallel, the best way is to control the process by changing the cost threshold for parallelism. So if we execute this, let's see that setting. So there is another setting. which is cost threshold for parallelism. Right now, it is set to 5. Maximum setting can be 32767. So the cost threshold for parallelism is 5 here, right? Which is a default value. The default value 5 is extremely low for most systems, and Microsoft generally doesn't agree. Uh, but we would like to make this value higher, right? Again, the precise value comes down to your system queries and load. Depends upon the load on your system, the queries that are being executed. That is how you set the cost threshold for parallelism. And we can change this setting using the same set of command using the execute sp configure. We can specify this setting over here like this. We can specify it like this, and we can configure the any threshold over here. Let's set it for 35. But yeah, we are not executing these changes. But yeah, we can change the cost threshold for parallelism here as well. Now, one of the ways to determine a good value for cost threshold would be to look at the estimated cost of the queries on your system. All right. And using that, you can set the cost threshold over here, right? So let me show you if we had executed any query. So I was talking that one of the way to determine a good value for cost threshold would be to look at the estimated cost of the queries in the system. So what is the estimated cost of this query on the system? Is it given on the select properties? So estimated cost is somewhere given over here. How much is the estimated cost? And depending on that, that particular value should be configured over here. The cost threshold for parallelism. Right now, let's leave this setting. Uh, Now, using any of the query metrics available and the cost estimates from execution plans, you can see how your systems are behaving and make adjustment from there to this particular value. All right, to see any performance benefits, right? So we need to check the query metrics like I was showing to you before. You can check the select metrics over here. These are some of the query metrics given over here. We will talk about them in detail later. For now, I think let's leave it. Let's close them and come back to the setting here. So we use the query metrics available and the cost estimates from execution plan to determine the value for this particular setting. And we basically see how our systems are behaving and make adjustment to this particular value, cost threshold for parallelism from there. All right. It was discussed earlier that the parallel execution is an expensive operation. We have indicated it here. So let me write more on it. So parallel execution is an expensive operation, right? Now, parallel execution doesn't just take up more CPUs, but also considerable more memory intensive. So how it is costly? The parallel execution doesn't just take up more CPU, but it will also take, but also considerably more memory as well. So it will take more CPU as well as more memory. And because of this, SQL Server will take into account the amount of available memory. So because of this, as it utilizes memory as well, the parallel execution needs memory. And because of this, SQL Server will also take into consideration, take into account or consideration the amount of memory available. I had highlighted this as one of the factor for parallel execution, for consideration for parallel execution, how much memory is available to the SQL Server. All right, so that is why, because the parallel execution also needs memory. So SQL Server takes into account the amount of memory available to it prior to executing a parallel plan. All right, and SQL Server will automatically reduce the amount of parallelism or abandon it entirely for a given query on a system under stress. So that's another important point. SQL Server automatically reduce the amount of parallelism or abandon it totally or kill it totally for a given query if your system is under stress. All right, on a system under stress. So if there is quite a load on the system, the SQL Server automatically will reduce the amount of parallelism. So keep this in mind. And now all the DML queries or data manipulation language queries are executed serially. However, the select in and insert and the where clause of update or delete statements can be executed in parallel. So we were talking about all data manipulation language queries where we are creating table or doing stuff like that. All these queries are executed serially and not parallelly, right? These cannot be parallel manner, I would say. So these DML queries, any of the DML queries cannot be executed in parallel manner. Some of the exceptions are select in and insert. So if we're doing any insert operation, which is a DML operation, so that can be executed in parallel fashion. And second example is where clause of update. So if we are using the DML query update query, and we are using the where clause, that queries can be executed in parallel. So where clause of update can be executed in parallel, or delete statements can be delete statements can be executed in parallel. So below DML's statements can be executed in parallel. So select clause inside an insert statement, where clause of update statement, and any of the delete statements. These can be executed in parallel. Now at an execution time, SQL Server can change the behavior of parallel execution, right? It then sets the number of processing threads for a given query, and that number of threads is used throughout the execution. The value can be re-examined at next time, re-examined the next time the query executes, and may change. All right, so at the execution time, first of all, the SQL Server can change the behavior of parallel execution. That is one fact. It can also set the number of processing threads that will be used by the query on a execution by execution basis. So keep these points in mind. Now we will talk about execution plan caching. So what is an execution plan uh, caching? That is the next topic. So let's focus on this. Let me mark it with the header. Let's take a different color. Now, when the optimizer completes its processing, all right, the result is an execution plan. So when the optimizer completes its processing, the result is the execution plan. So execution plan gets generated once the optimizer finishes its operations. Now this plan is saved in the memory of SQL Server. all right, in a place. So once this plan is generated, it gets saved in the memory of SQL Server in a place which is referred to as the plan cache. So all the execution plans are saved in the plan cache. Now, what is the benefit of saving the plan into a cache? Saving the plan into the cache is another optimization. So this is another optimization operation, right? Saving the particular execution plan into a cache. This is another optimization that SQL Server performs in an attempt to make your queries faster. So if the query execution plan is in the plan cache, so when every time or the next time if you execute the same query, it utilizes the plan from cache, and the processing operation will be faster as the optimizer does not have to generate the plan altogether, but instead it can use the already created plan from the plan cache, right? So that is how it utilizes the plan cache to fetch the execution plan to make the queries run faster in the next execution time. All right. Now let me describe this. Now by saving the plan, right, that plan can be reused, right, instead of going through the optimization process again to generate the plan again, right? We don't have to go through optimization process once again because as the plan is already cached, that plan can be used immediately. Now, although the plans are saved to the plan cache, however, plans can be removed from the cache through various processes. One of these processes is referred to as aging. So aging is one of the process that removes the execution plans from the plan cache. So if an execution plan becomes quite older, the aging process will remove that plan from the plan cache. Now let's talk about the aging of the execution plan, which is the last topic. So let me cover that. Aging of the execution plan. This is the next thing, and let me highlight it as the heading. Let's take some other. Let's take it as this. So, what is this plan cache? The plan cache is part of SQL Server buffer cache. So it stores the plans inside SQL Server buffer cache. And this buffer cache also holds the data pages, which also holds any data pages, right? Now, as new plans or new execution plans, I would say, are added to the plan cache, right? The size of the plan cache keeps growing, right? So as often we start adding plans, or as soon as the query optimizer start adding plan to the plan cache, the plan cache keeps on growing, right? Growing in size, and basically that affects the retention of useful data pages in the memory. So storing the plan in plan cache affects the retention of useful data pages that are also stored in the buffer cache or plan cache memory. All right, and to basically avoid this, so that data pages should not get removed from the plan cache upon add operation of execution plan to the plan cache. To avoid this situation, the SQL Server dynamically controls the retention of the execution plans. So SQL Server dynamically controls the retention of the any of the execution plans, all right, in the plan cache. So it totally depends upon the SQL Server, how often or for how long it wants to keep the execution plan in the plan cache. And basically, it retains the frequently used execution plans. It retains any frequently used execution plans and discards any plans that are not used. Discard any plans that are not used for a certain period of time. All right. So if any of the plans are not used for a certain period of time, SQL Server basically discards them and removes them from the plan cache. And basically, how it does that? How does it decide that a plan is used frequently or not? So SQL Server basically keeps the track of the frequency of an execution plan. So it keeps track of the frequency of an execution plan's reuse, right? By associating an age field to it. So it associates an age field with the plan, right? So whenever the plan is used next, the age field gets updated, right? So it basically uses the age field to track the frequency of execution plan reuse. Now, when an execution plan is generated, right? The age field gets populated. The age field is populated with the cost of the age field is populated with the cost of generating the plan, right? So a complex query that requiring extensive optimization. So if we have any complex query that requires an extensive optimization, we'll have an age field value higher than that for the simple query. All right. So let me go through it again. So SQL Server basically keep tracks of the frequency of execution plan reuse by associating an age field to it. And what does this age field contains? So when an execution plan is generated, the age field is populated with the cost of generating the plan. And this age field value is higher for the complex queries and lower for the simple queries. All right. And because the cost of generating complex query execution plans are much more than generating the query plans for the simple queries. All right. Now what happens at regular intervals? The current cost of all the execution plans in the plan cache is examined by SQL Server lazy writer process. So keep this in mind. There's a lazy writer process for SQL Server, which basically at regular intervals checks the cost of all the execution plans which are there in the plan cache, right? And this lazy writer process manages which manages the most of the background processes in SQL Server. All right. So the SQL Server lazy writer process check at regular intervals the current cost of all the execution plans, right? And if an execution plan is not reused for a long time, so if an execution plan If it finds that an execution plan is not used for a long time, right, then the current cost will eventually be reduced to zero. So basically, the role of lazy writer process is to reduce the cost field of the execution plans that are not being used. It reduces the cost of those plans gradually, ultimately reducing it to zero. All right. So the cheaper the execution plan was to generate, which is for a simple query, the sooner its cost will be reduced to zero. Now, once the execution plan's cost reaches zero, all right, the plan becomes a candidate for removal from memory or plan cache, you can say. So if the its cost becomes zero in the age field, the plan becomes candidate for removal from the memory. Now, SQL Server removes all plans with a cost of zero from the plan cache when memory pressure increases on the system. When memory pressure increases to such an extent that there is no longer enough free memory to serve new requests. So if there is no memory available in the system to serve any new request, at that time SQL Server runs its lazy writer process and checks all the execution plans, their age field, to see if any of them has reached zero. So it removes all the plans with a cost of zero from the plan cache whenever the memory pressure increases on the system. Now, however, we have talked about the situation where the system has less memory. However, let's talk about the scenario if a system has enough memory, right? What does the SQL Server do in those situations? So if a system has enough memory and free memory pages, right, to serve new requests, right? Execution plans, then at that time, execution plans with a cost of zero, right, can remain in the plan cache. So it happens only in the situation where we have enough free memory available in the system. Only at those times, the execution plans with a cost of zero can retain or remain in plan cache for a long time so that they can be reused later. All right. Now the role of SQL Server lazy writer process is to change the cost downwards. Execution plans can also find their cost increase to the max cost of generating the plan every time a plan is reused. So whenever a plan is reused, it increases the cost of the plan. All right. So SQL Server lazy writer process also adds to the cost of the plan in case the plan is reused quite oftenly, right? So execution plans can also find their cost increase to the max cost of generating the plan every time the plan is reused. So whenever a plan is reused, it basically the age field or the cost field is written on the plan. Basically, it increases that process increases the cost of the plan which is being reused. Now, for example, let me explain it through example. For examples, suppose you have two execution plans, right, with generation costs equal to 100 and maybe 10 for another plan. So one plan has a cost of 100, another plan has a cost of 10. Their starting cost values will therefore be 100 and 10, right? Now, if both execution plans are reused immediately, so we are talking about the situation where both the execution plans are reused immediately, their age fields will be set back to the maximum cost. So whenever a plan is used or reused, their aging field is set back to the maximum cost. All right. And with these cost values, the lazy writer, which is a SQL Server process, will bring down the cost of the second plan to zero much earlier than that of the first one with cost 100. All right. Unless the second plan is reused more often than the first plan having a cost of 100. Therefore, even if a costly plan is reused less frequently, so if a costly plan, if we talk about, is reused less frequently than a cheaper plan, because of the effect of the initial cost, the costly plan can remain at a non-zero cost for a longer period of time. Alright, because of its cost, it can remain in the system for a longer period of time. So guys, I hope you got this idea. So let me write this line as well. Therefore, even if a costly plan is reused less frequently, then a cheaper plan, right? So even if a costly plan is reused less frequently than the cheaper plan, and because of the effect of its initial cost, which was higher, right? Which was higher, right? The costly plan can at a remain at a non-zero cost value for a longer period of time. That is mathematics basically. So that is fine and it's absolutely understood. So guys, I hope you got the idea. And guys, we are done with this topic. Give me a few minutes. So guys, what we have seen here is we have talked about the query optimizer in this video. So basically, query optimizer is used to make your queries run faster. We have gone through the basic process that the optimizer goes through, from parsing till binding, through to matching with the trivial plans, and finally into the full optimization process. And we have discussed upon how the parallel plan works and the ways in which execution plans end up in the plan cache and how they get removed from the plan cache. and I hope you like this video. We have covered the optimization process in detail over here. So query processor tree is fed to the optimizer. We have discussed about the optimization process. All right, and we have talked about the parts of optimization process where simplification is done, query simplification is done, then the trivial match happens, then the query text pass through the optimization phases, which are three phases. All right, search 0, search 1, and search 2. And we have taken you through a dynamic management view as well to get the query optimizer info. We have shown you some practicals as well to check some of the execution plans to see the work done by the optimizer. We have also talked about the generation of parallel execution plans and what are the factors the optimizer considers before taking the query in a parallel execution mode. We have talked about that. We have talked about the execution plan caching process and how the plans get saged out from the plan cache and how they got removed by the SQL Server lazy writer process. So guys, this is a quite knowledgeable video. I would request you to please go through it at least 2 or 3 times to gain better understanding of the optimization process. So I thank you so much for your time on this video, guys. Let me take you to the screen. This was the past part 2 of query execution plan generation process and query optimization. These are 2-part videos, so please check out the previous part as well. Thank you so much for your time on this video today. Please share your comments with us, guys. If you are new to this channel and if you have not already subscribed to my channel, there is a subscribe button below this video. Click on that subscribe button. It will give you a bell icon. Click on that bell icon, select all notifications to get notifications regarding all my future videos. And also, guys, please do share your comments, your suggestions, your requirements. I will be creating more videos on performance tuning soon, as there is a demand for performance tuning videos. I will be creating much more soon, and if you have any special requests, do let us know. Also, guys, share your day-to-day experiences with SQL Server. Let us know about the situation where my videos have helped you in under any circumstance. And also, guys, please share this video with your friends if you feel this video is useful for them as well. And also ask them to subscribe to my channel. If you feel that my videos can make difference in their life, then please do ask them to subscribe to my channel. I would be very thankful to you. Thank you so much for your time once again on this video, and you have a wonderful day, guys. Thank you.